So I'm going to resolve this problem that I solved for you yesterday during class. And if you are struggling with the new problem I've given you with only 2 isotopes, then I would encourage you to try to work through this one in its entirety with me on a piece of paper, and then use that example and that process to apply it to the next problem I've given you. So we're going to start here with the prediction all over again, because prediction's pretty important. It allows you to verify if your answer is ballpark correct. And we said yesterday that the calculated value should be closest to 39. Remember, this is an average. So if everybody in our classroom weighs between 100 and 200 pounds, we wouldn't expect the average weight to be above 200 or below 100. So just based on what an average is by definition, it should be somewhere between 39 and 41. But even we can get more specific because this is a weighted average, which means the actual numerical average will be most similar to the mass number of the isotope with the highest abundance. The mass number of the isotope with the highest abundance. So here, 93.2 is far outweighing the other abundances. And that means that the average that we calculate should be closest to 39. And that is the primary thing you're looking at when you're making your estimations. Now, if you come out with an answer that is 36 or 41 or even 40.5, you know that that can't be right because your weighted average pulls closest to 39. And that's how the prediction helps you. But in actually completing the calculation and identifying what you have going on, recognize that there are only 2 variables here. There is mass and there is abundance. There is mass and there is abundance. There is mass and there is abundance. So we're looking at 3 different masses, 3 different abundances. These each represent each isotope. So we have isotope 1, we have isotope 2, and isotope 3. Okay? Which one's isotope 1, 2, 3? Doesn't matter at all. And to prove it, I'm going to do it the opposite of how I have the example worked in the image above, where I have, isotope 1, isotope 2, and isotope 3. Okay? It doesn't matter if my most abundant is 1, 2, or 3, just so that we combine the mass and the abundance of one isotope together. Now, if all we need is mass and abundance, that means our number of protons and neutrons don't matter to us at all. That's just extra information here. But you need to recognize that, and you shouldn't expect to not be given extra information. I might be able to give you extra information, and you need to know what you need to use to solve for an average. Now, a common mistake is to use the mass number instead of the atomic mass. When you're given both, you do not use the mass number. The mass number is an estimate, and it's a reflection of counting particles of a nucleus. It is not actually a mass. We have actually a measured amount. If you're given the atomic mass units, you should use them. If you're not given the atomic mass units, it's sufficient to use the mass number. We'll give you an estimate of the average, but it will be considerably different as a final response or a final answer. Because look at all of the decimals, that you would be leaving off there. It's considerable. So for those of you out there and said to me yesterday, I don't know what to use. What is this information? A is abundance and M is mass. So we have abundance and mass. So if we're going to label this, we go abundance and mass. So there's my A and my M, and that's where these numbers are all coming from. Now, if I need an A and an M for isotope 1, that means I need these 2 numbers together. And if I need my isotope 1 is going to be arbitrarily down here. If I need an A and an M, an abundance and a mass for isotope 2, there it is. And an A and M for isotope 3, there it is. Now, what this equation tells me is that I'm multiplying together the A and the M. So quite literally, I could simply do this, recognizing that I can get 3 subtotals and add them together. That's all we're showing here. But I am going to go through substituting the entire problem so that, I didn't realize my microphone wasn't near me. Sorry about that if you couldn't hear me. I'm going to go through the entire problem so you can see them substituted. All right, first we are going to pay close attention to isotope 1, mass and abundance. Abundance starts with the letter A. Mass starts with the letter M. So we go, abundance in mass is 40.962 multiplied by the 6.7302. And there's my isotope 1. If you need to label them throughout your calculation to keep them correct and keep them straight and know what you're doing, by all means do that. We have isotope 2. Now we're not looking at that bottom set of data anymore. Now we're looking at isotope 2 mass and abundance data. We have 39.964 multiplied by 0.0117%. And that's our isotope 2 information. And finally, isotope 3, mass and abundance. That's our information at the top there. 38.9637 multiplied by 93.2581. There we go, isotope 3. Now, our equation says we have to subtotal all that and divide by 100. You may use a calculator, set up in the calculator exactly this way with parentheses, divide by 100 at the end. If you're like me, that can get messy and you can't really find where you made a mistake or easily go back and delete. So what I'm going to do is I solve these for you is I'm going to subtotal each product and then we're going to look at the way that goes. So I'm pretty sure you can see my entire screen here. I'm going to do 40.962 multiplied by the 6.7302 and I got 275.6824. So that's my isotope 1. Abundance times mass. Now I need to do isotope 2. Isotope 2 is 39.964 multiplied by the 0.0117. And I get 0.4675. How do I know how many decimal places to keep, Mrs. Crosis? Keep 3 or 4. There are rules to help us determine that, but we're not learning those because we simply just don't do enough math to warrant it. Isotope 3, here we go, 38.9637 multiplied by the 93.2581, and we get 3,633.6806. 3633.6806. This is an answer a lot of folks gave for the final answer yesterday, and they just didn't work it all through. Okay, so those are my subtotals. See, I've tried to carry it through for you here. This is isotope 1, mass abundance. Isotope 2, mass abundance. Isotope 3, mass abundance. I have multiplied each of them. Isotope 1, 2, 3. Now we have subtotaled them. Isotope 1, 2, 3. We're going to add them together and divide by 100. We should come up with an answer that we can verify on the periodic table. Let's see. 275.6824 plus 0.4675 plus 3633.6806. Divide me by 100 and I get 39.0983. And that's going to be atomic mass units. Now, I'm going to open my periodic table, webelements.com, and I'm going to look for 35, what was it? 39.09. We can actually find, I'm going to grab a snip here. The potassium has an average atomic mass of 39.098. Okay, so average atomic mass can be used to identify elements because the average atomic mass is found beneath the symbol on the periodic table. So we can double check our work that way. And we could use our prediction too. Our final answer did come out very close to 39, 39.0. And some change. Now, if you use the mass number instead of the actual atomic mass, you may not so easily be able to identify the element with the periodic table because the masses of neighboring elements are quite close to one another. So to be off a few decimal places is pretty significant. All right, now you take this example and apply it to this question, which is where you're picking up today, whether you didn't try yesterday or whether you tried and got stuck, maybe hopefully somewhere in the mix there. I clarified part of the process for you. Heads up, 7 up, you have A, abundance, M, mass. The mass number is useful here in naming your isotopes. That would be a good thing to do, but it doesn't have to be used in the calculation. I will be keeping tabs on you throughout class today. Please be sure to communicate with me, but really I want you to try. Let me see what you can do if all you can do is identify variables and label them and sub them into an equation. If you want me to check you at every step of the way, I certainly will, but I'm not going to work the problem for you. You're going to show me what you can do, and that's how we're going to play this. I know you can do it. Good luck.